divided by 122.1 grams per mole.
Oh.
There we go. Okay. Then the initial concentration of sodium benzoate would be the same, except you use 144.1. So 4 divided by 144.1, and we get 0.028. Okay, initial concentration of hydrogen protons is 0. So equilibrium is going to shift to the, which way? It's going to shift to the right, yeah? Because you have more, you have the concentration of sodium, of benzoic acid is 0.33, which is greater than both the concentrations of the products. So concentration is going to shift to the right. So this is going to be plus X, minus X, 0.033 minus X, 0.028 plus X, and X. Okay. So we can say then that pH is going to be equal to the pKa, 6.3 times 10 to the minus 5, plus the log of the base, which is benzoate, 0.028 plus X, divided by 0.033 minus X. Now that looks bad. I wouldn't want to have to solve that in a final exam. Right? So what can we do? We can make an approximation here, right? Yeah?
The 6.3 times 10 to the 85, isn't that the Ka?
It is the Ka.
The Ka?
Oh, you're right. I'm sorry. Thank you. Good catch. Okay, so 6.3, so we take the negative log of 6.3 times 10 to the minus 5. .2. Okay. So since we're saying that 6.3 times 10 to the minus 5, that's pretty little. So we could assume then that X is going to be small compared to both of 0.033 and 0.028. So we could basically assume that this whole side is roughly equal to 0.028 divided by 0.033. We can make that assumption. And so then we can say, okay, so then the log of 0.028 divided by 0.033. So then we can get the log of 0.85. Something like that. Yeah.
Why didn't you make the assumption that X is going to go away?
Because your Ka value is very small compared to your the concentrations of both your acid and your base. So the Ka value is something times 10 to the minus 5, and your concentrations are something on the order of 1,000 times bigger than that. Yeah?
So is it really necessary for us to fill out the ice table?
No.
Okay. I was just
No, you didn't have to do it at all, but I was just doing it so that you could see that for yourselves.
Okay.
Okay, so you get, if you do this, you get 4.13. This one. Any other questions on that? Yeah.
If Ka is smaller, do we have to do the ice table?
If K is larger, you mean?
I mean, yeah, it's larger.
Yes, but it probably won't be. I don't think you would have to integrate the Henderson-Hasselbalch equation into an ice table on the final.
Okay.
Yeah, because if you did have to integrate it, you'd probably have to solve something like this,
Yeah.
which is a challenging thing to solve. Okay, any other questions? Moving on. Okay. I'll let you start.
All right, so problems on the exam don't necessarily have to be all really involved. I've got a couple of ones that should be pretty quick if you can interpret them the way they're supposed to be interpreted. So, what is the pH of a 2.0 times 10 to the negative 4 molar solution of HCl? HCl is a strong acid. So what do we know about strong acids in solution? Right, they completely dissociate, so they alter into protons. So, given this number, what we should be able to do is just take this and turn it into pH, because that molar applies to the protons that will be released into solution when you dissolve the HCl. Right? So pH is just equal to the negative log of H plus, right? And H plus is this number over here. And so all you have to do is just type in negative log 2.0 negative 4, we get 3.69 roughly, which reduces to 3.7. Yes?
What if it was a weak acid?
If it was a weak acid, it gets more complicated. If you're asked to calculate the pH of a weak acid, it's basically like a buffer, unless there are other conditions given. So you use the Henderson-Hasselbalch equation, and they give you more information. This one is convenient because if you see a strong acid, it's asking you for pH. It should be pretty straightforward. I think with that, we're moving on to the exam 3 material, the final stretch here. Here's another little short one. Kind of a you know it or you don't. But you should have the laws of thermodynamics. The third law of thermodynamics states that A, the total mass / energy of the universe is constant. In any spontaneous process, the total entropy of the universe increases. The entropy of a perfect crystal at 0 Kelvin is equal to 0, and the vapor pressure of the liquid in solution is proportional to its mole fraction. And then, a little jokey answer, the amount of work expended to fill the time available. If you know this is Murphy's law, which isn't really a law. So, as far as eliminating these goes, we can eliminate E off the bat because it doesn't really have to do with chemistry. And so the first 3 of these are the laws of thermodynamics. We know this last one doesn't really have a whole lot to do with thermodynamics in its formal sense. This is actually Raoult's law. Right? So we can eliminate that. And these are pretty much stated in order, right? Total mass energy of the universe is constant. That's energy created and destroyed. That's the first law. Spontaneous process, entropy increases. That's the second law. This one right here is the third law of thermodynamics. They don't all have to be tricky, but be prepared for the tricky one. So we followed that so far. Strong acids and the laws of thermodynamics. ready to go? Yeah.
Okay. Okay, for a system at equilibrium, choose the best answer. Delta G greater than 0, delta S universe equals 0, delta G less than 0, delta H greater than 0, delta S system greater than 0, E cell less than 0, K greater than 1, or more than one of the above is correct. You say you don't like it?
No, I like that question.
Okay. You said he likes that question. I don't like this question. Okay, so we're at equilibrium. So, do we know anything about whether delta G is positive or negative or 0? Nope. Don't know anything about the system other than we're at equilibrium. So we know that at equilibrium, delta G equals delta G naught, right? But other than that, we don't know. So, we don't know anything about delta G, and we don't know anything about delta H, and we don't know anything about delta S for the system. So, when I do this, I would say, okay, so I know I don't know anything about delta G, so we can cross that one out, and that one out. And we don't know anything about delta H, so we can cross that one out. Do we know anything about the voltage potential of the cell? Nope. Just that it's at equilibrium. That means that Q equals K. That's all we know. So then, we don't know that one. We don't know the equilibrium constant. We know that Q equals K, but we don't know what either one of those are, so we can't say that one. Okay, so we're down to delta S system is greater than 0, or the delta S universe is equal to 0. So, delta S system greater than 0 isn't true, because we don't know what the entropy change of the system is. Now, we know a second law of thermodynamics says the entropy of the universe is always increasing, right? So that's where I kind of have an issue with this one, because it says, well, okay, so this is delta S of the universe is equal to 0 only in that little system of the reaction. So it says, oh, okay, so you could say, yeah. Sometimes you get questions like this, though, where it's like, you don't feel real great about the answer, but that's your best choice. Any questions on this one? Okay.
So, consider the following equilibrium reaction. We have pentanol liquid turns into pentanol gas. So this is just we're boiling this stuff. Delta H for this reaction is 55.5 kilojoules per mole, and delta S for the reaction is 148 joules per full Kelvin.